Hello everyone. Now I am going to explain you about a topic on half-wave rectifier. So first of all, we'll know the basic definition of rectifier. So rectifier is a circuit which is used to convert the AC voltage into an pulsating DC voltage. Okay. So in that rectifiers, we'll see two different types. One is half-wave rectifier and full-wave rectifier. In full-wave rectifier, we'll see full-wave rectifier and a bridge rectifier. Now I am going to explain you about an operation of an half-wave rectifier. So consider, and so this is the basic circuit diagram of an half-wave rectifier. So it consists of an rectifying element as diode, and it has a one transformer. So which is a the function of the transformer is to steps up the source voltage either up or down. So here in this half-wave rectifier we use a step down transformer, and this transformer has a two windings. The first winding is called as a primary winding, it has N1 turns, and the second winding is called as secondary winding, it has N2 turns. So the input voltage 220 volts is applied to a primary winding, and that is changed to either 9 volts or 12 volts, and that is applied to a diode from the secondary winding. So this is the basic circuit diagram of an half-wave rectifier, and these are the input and output waveforms. Okay, now we will see the operation of this half-wave rectifier. So let us consider case 1. So this is the here I am considering the only positive half cycle. Okay, so this is a time interval from 0 to pi. So this is applied to this transformer of a primary winding. So this is of a 220 volts. So whenever you are applying this 220 volts 50 hertz signal from this transformer, so here the frequency may not changes, or the only the voltage will be either steps up or step down. Okay, so here we are applying a 220 volts at the primary winding side, and that is converted to either 9 volts or 12 volts to the secondary side. And here the diode gets, here we connected the forward biased diode. So for a positive half cycle, the diode gets forward biased and the diode acts as a short circuit. So the maximum current is flown through this load resistor. So here the output, the voltage developed across this load resistor is nothing but simply your input voltage. Output follows the input voltage. So for the positive half cycle from the time interval 0 to pi, you'll get the maximum output. So whatever the input here, so you'll get that as output. Okay. So now coming to the new negative half cycle, this is a case 2. For during negative half cycle, nothing but the time period pi to 2 pi. So in this one, the diode gets reverse bias and output voltage is 0. So this is the circuit diagram, and same here we are applying a negative half cycle. This is applied to this transformer. So here for negative half cycle, the diode gets reverse biased condition. It simply acts as a open circuited. There is no current, so there is no voltage developed across this load resistor. So hence the output voltage is 0. So for the negative half cycle for this region, so the output voltage is 0. So here only half of the input wave only rectified, so it is called as a half wave rectifier. Now we will see the some parameters of that half wave rectifier. So that parameters are like average current, average voltage, RMS current, and the AC power, DC power, efficiency, ripple factor. So first of all, here I am calculating the what is the average DC output voltage. So here the average DC output voltage nothing but the total area by the base. So first of all, the area is nothing but, so it is from 0 to pi Vm sin omega t d omega t plus pi to 2 pi Vm sin omega t d omega t. So in the time interval 0 to pi you are getting a maximum output. So V naught is equal to Vm sin omega t d omega t. But for pi to 2 pi, so in the pi to 2 pi region we are not getting any output voltage, so it will be 0. So it will be 0 here. So therefore integrate this equation. So it will be Vm will be constant here. So Vm 0 to pi sin omega t d omega t. So the integration of sin is nothing but minus cos omega t. And apply the limits. So Vm minus cos pi plus cos 0. And we know the value of cos pi is minus 1. So minus of minus 1 is nothing but plus 1 plus 1. So here we are getting a 2 Vm. So therefore the total DC voltage is nothing but 2 Vm by the total area is nothing, base is nothing but 2 pi, 0 to 2 pi. So it will be 2 Vm by 2 pi. So therefore it is Vm by pi. Similarly the average current or DC current is equal to Vm by pi into RL. Nothing but IDC is equal to VDC by RL. So here VDC is nothing but Vm by pi. So therefore IDC is equal to Im by pi. Similarly, the RMS value of the load current. So therefore, RMS is nothing but the AC component. The RMS is nothing but it is root mean square value. So which is equal to under root of 1 by 2 pi 0 to 2 pi Im sin omega t whole square d omega t. And we know it has a two intervals from 0 to pi and pi to 2 pi. And we know from the pi to 2 pi interval we are not getting any output voltage or output current. It will be 0 here. So this is will get cancelled out here. So therefore, IRMS is equal to 1 by 2 pi. So here Im with respect to d omega t, Im will be constant. So make it as outside. So Im square 0 to pi sin square omega t. And we know the value of sin square omega t is nothing but 1 minus cos 2 omega t by 2. So therefore, here I am writing this term Im square by 2 pi 0 to 2 pi 1 minus cos 2 omega t by 2. By upon integrating this, we will get this equation Im square by 4 pi 2. So constant of integration is nothing but omega t minus cos of 2 omega t integration is sin 2 omega t by 2. And apply the limits. So and we know that sin pi is 0, sin 0 is 0. So this term will get cancelled here. So you'll get only the term only pi. So it is Im square by 4 pi into pi will get cancelled, you'll get the term Im by 2. So the total RMS value is Im by 2. Similarly, the RMS voltage is Vm by 2. Okay. I will calculate the AC input power or AC power input, which is denoted by a term PAC. So PAC is equal to the total current I square into the resistances. So the load resistance and the diode will get forward biased, so it has some forward resistance. So therefore the AC power is equal to I square RMS into RL plus RF. So therefore substitute that IRMS as Im by 2 here from the equation 4. So PAC is equal to Im square by 4 into RL plus RF. Similarly, the DC output power, so which is denoted by a PDC. So PDC is equal to VDC into IDC, and we know VDC is Vm by pi, IDC is Im by pi. Upon substituting that values, we are getting Im square by pi square into RL value. And the next term will be the efficiency. So the efficiency of rectifier, which is nothing but the output by input value. Here the output is a DC power, input will be the AC power. So it is PDC by PAC. So just now we solve this one. It is Im square by pi square into RL. PAC is Im square by 4 into RL plus RF. So upon simplifying this, we'll get eta is equal to 4 by pi square into RL by RL plus RF. So here I am making the term RL as common. So we will get 4 by pi square into 1 plus RF by RL value. If RL is much greater than RF value, neglect that RF by RL term. So therefore eta is nothing but 4 by pi square value, which is equal to 0.405. So in terms of percentage, eta is equal to 40.6. The efficiency of half wave rectifier is 40.6. And the next one is the ripple factor. So ripple factor is nothing but how much of the AC component is presented in the DC output. Okay, so this is AC component present in the DC output. So V dash RMS by VDC, which is equal to I dash RMS by IDC. So this is a basic equation. The ripple factor gamma is equal to under root of IRMS by IDC whole square minus 1. So from the equations 1 and 2, 3 and 4 will got these values. So I have a RMS is I square by 2, think but Im square by 2. So upon substituting that values we will get gamma is equal to 1.2103 in terms of percentage. So gamma is equal to 121.03, nothing but, so in the half-wave rectifier 120% of AC component is presented here. So this much of the AC component is presented in the half-wave rectifier. So we always go for full-wave rectifier or bridge rectifier. And the next one is a peak inverse voltage. So peak inverse voltage is nothing but the voltage presented across a diode when it is gets reverse biased. So when the diode gets reverse biased, it stores the maximum peak voltage is Vm, because it is this value is stored when it is gets forward biased condition. And the next one is the transformer utilization factor TUF, so which is equal to PDC by PAC rated value. So PAC is nothing but VRMS into IRMS value. So we know that this value PDC is Im by pi whole square into RL. So here we are taking the VRMS as Vm by 2. Generally it is Vm by 2. But here we are taking it is rated one. So it will be Vm by root 2 into IRMS is, we always take the RMS value as current is same. So it is Im by 2. So upon simplifying this we will get TUF is 0.287 or 28.7 percentage. Thank you.